Hello dear students! This is Tamás Jávor. Welcome to Rubber Duck Physics. Today we begin learning about the chapter on Galilean and special relativity. The difficulty and topics of this series should cover the IB Diploma Program Physics Higher Level chapter, but you can make use of it whatever purpose you study relativity for. This is one of the most challenging topics in the whole DP Physics syllabus, so in this video we'll just get familiar with the new terrain. How and why is the topic of special relativity difficult? Well, so far, in Theme A, Space, Time and Motion, you have been learning about concepts that are pretty intuitive. What does intuitive mean? Let's go most conveniently to the free online Wiktionary and find the definition of the word. Intuitive, as an adjective, means spontaneous without requiring conscious thought, or easily understood or grasped by intuition. Of course, what intuition is then remains a question, so let's turn to that article as well. Intuition is defined as immediate cognition without the use of conscious rational processes. So why do we call kinematics and Newton's laws intuitive? Because you could easily imagine from your experience of moving objects what speed is, what acceleration is, and what a force is. Although some ideas, like Newton's first law of inertia about forces not needed to keep up motion, did require a conceptual shift, and some quantities like energy were a bit abstract, none of the objects in Newtonian mechanics behaved in ways that felt unnatural. With practice, the laws of motion became something you could accept by intuition. And so will be the Galilean principle of relativity, which we will discuss in the next video. It is just an extension of Newton's view on motion, describing how the position of an object changes when observed from different reference frames. But things changed at the end of the 19th century. Physicists, and let's not discredit them, mathematicians, began studying the motion of light through space. And they were forced to radically rethink their ideas about space and time. Their findings were completely counterintuitive, the opposite of intuitive. Counterintuitive means contrary to intuition or common sense. Suddenly, the idea that distances between points or even time between events could depend on who is observing them became unavoidable. They found that the speed of light was independent of the motion of its source. Our everyday intuition about space and time collapsed. The scientists of the turn of the 20th century first tried to patch these findings by questioning the experiments themselves, or they tried to convince themselves that something in our understanding was wrong, but then came Albert Einstein. It was he who first reconciled these mind-blowing results with how humans had always experienced the world. And interestingly, intuition itself played a role in his discovery. But here, we mean intuition in a different sense. If we go back to Wiktionary, another definition of intuition is a perceptive insight gained by the use of this faculty, where faculty stands for ability or skill. Good morning, Professor Einstein. Thank you for your theory. We really appreciate your intuition. Einstein could not deduce the foundational statements he made about relativity from existing knowledge. Instead, after long and careful thought, he realized that to match experimental and conceptual results while preserving common sense, these conditions, only two of them, were logically necessary. That's why we call them postulates, a concept we will explore in a later video. This realization is what showed his genius and made him remembered to this day. So, why didn't humanity discover relativity earlier? Because we never had direct experience with objects moving at speeds close to that of light. At ordinary speeds, the effects of relativity are so small that we never noticed them. Mathematically, special relativity is not too difficult. The most advanced formula you will need involves a function of v squared with a square root. The hard part is the conceptual shift. Can you let go of your assumptions about space and time? Assumptions built from your own experience, from the time you first moved as a baby to your most recent physics experiments. Are you prepared to accept that while not everything is relative, distance and time are? The consequences of accepting Einstein's postulates extend far beyond space and time. They impact our understanding of momentum, energy, mass, even electric and magnetic fields. But in DP physics, we will focus only on how relativity reshapes our concepts of space and time. This was probably the greatest paradigm shift in physics, yet it was accepted by the scientific community in just a few decades. We will begin our journey by exploring Galilean relativity, how different observers describe the same motion. I invite you to think about this question until the next video. Tonight, you go to sleep in your bedroom. Some two cheerful friends of yours come in and carefully move your bed on board a spacecraft, making sure not to wake you up. By the time you do wake up, you are inside a windowless cabin and the spacecraft is moving at constant velocity. How can you verify if anything changed? Can you determine whether you are moving, and if so, at what speed? That was the introduction to Galilean and special relativity. Let's summarize the main points. 1. Everything you have learned about mechanics so far was fairly intuitive, and so will be Galileo's principle of relativity. But Einstein's relativity breaks intuition. 2. The study of light led physicists to irresolvable paradoxes by the end of the 19th century. Einstein's key insight was that instead of rejecting these paradoxes, we must accept a few new fundamental statements about space and time. 3. These characteristics of space and time were always there. We just didn't have a way of discovering them earlier. Now that we do, we must acknowledge them to complete our understanding. 4. If you can make this conceptual shift, the mathematics of relativity will not be difficult. If you are looking for a real mathematical challenge, then general relativity is what you need, though that is beyond DP physics. If you want to develop a deep understanding of relativity or any other high school physics topics, I also provide one-on-one tutoring online. I tutor IB/DP physics, A-level physics and mathematics, and AP physics, helping students strengthen both conceptual understanding and problem-solving skills. If you are interested, you can find my email address in the channel data of the Rubber Duck Physics YouTube channel. It's visible only if you view it on a computer browser. I look forward to working with you. Thank you for watching Rubber Duck Physics. See you next time.